Now that we have a definition of differential equation and initial value problem with us, we can now proceed based on the remarks that I gave you for the definition of differential equation. The remark was very simple that it is very easy to construct an example of differential equation. However, it might be very difficult to solve differential equation. In many cases, if I write differential equation randomly, it's highly likely that I will not be able to solve it. So we would like to focus our attention on a very special type of differential equation whose solution technique is known to us. Alright. In this particular course, you are going to see two very special type of differential equation whose solution technique is known to us. So let's begin with the first type of differential equation whose solution is known to us. We are going to call this differential equation a separable DE. So let's first introduce what do we mean by separable differential equations. So here is the definition of separable differential equation. A differential equation of the form dy by dx equal to function of x times function of y. Alright, this is a very special type of right side function where the right side can be seen as a product of function of x and function of y. Alright, if you have differential equation in this form, then we would like to call it separable differential equation. Alright, as I said earlier that most of the names in mathematics, they are given based on the logic used in that definition. Clearly this is a perfect name for this type of differential equation. You can separately see the variables involved in the function of two variables, and this is the reason why this type of equations are called separable differential equations. Alright. I would like to give you initial value problem form, so IVP form. It's a differential equation with associated initial data. Alright. So often you have seen function written in this format, y equal to f of x. For the very first time, we are writing our function in this format. Y is function of x. Alright, so understand that this is really like the same old notation of a function that you were using. The bracket inside value refers to the value of x, the right side value refers to the initial value of y. Okay. Now let's first try to see few illustration if we can recognize if the differential equation is separable or not. Okay, so these are kind of very simple type of problems. It's a determine if each of the following DEs or differential equations are separable or not. Alright, so here is the first example. Let's say I give you this differential equation dy by dx equal to 3x square plus 4x plus 5. Alright, Here is the second one. Dy by dx equal to, let's say simply x plus y. Dy by dx equal to 2x square e to the y square plus 5. Dy by dx equal to, let's say we have 3 over 2y plus 5. Dy by dx equal to x square plus x square y plus 2y plus, let's say 2. Alright, and then perhaps one more, dy by dx equal to 2x cube plus e to the x plus y plus y cube. Alright, we would like to see if the right hand side of our differential equation can separately be seen as a factor, pure factor of function of x and pure factor associated with variable y. Alright, so seems like in the first example it looks like I have this second degree polynomial in variable x. We can always assume that it is multiplied by a constant function of y. Alright, so meaning that this right hand side can be seen as a function of variable x multiplied by function of variable y. This is a separable DE. Alright, for the second example, as you see, I have right side function as x plus y. There is no way that I can convert this right hand side in form of two factors where one factor is purely dependent on variable x, the other factor is purely dependent on variable y. So this differential equation, even though the right hand side looks pretty simple, it's not separable DE. Alright. In the third example, this is a separable differential equation. Clearly we can see variable x and variable y separate in terms of their product. Alright, so this is a separable DE. The fourth equation, DE, it's similar to very first one. Function of x is missing. You can always assume that function of x is a constant function, and then you have function of y multiplied with it. So this is a standard example of separable DE. Now let's carefully look at problem number 5. In problem number 5, seems like right hand side is a sum of various terms. There are 4 terms indeed. Alright, in order to figure out if this is a separable differential equation or not, what I want you to do is try to use the standard factorization technique to see if you can convert this 4-term expression in form of a factors where one factor is purely dependent on x, the other factor is purely dependent on y. Not saying that this is possible for every expression of this form, but at least we would like to try and check if that can be done or not. If that can be done, then we have a method to solve it. If that cannot be done, then we don't know if we have other method to solve it or not. Well, let's try to use the standard factorization technique. Seems like if I group the first 2 and last 2 terms and factor x square out from first 2 terms, I get 1 plus y. If I factor 2 out from the last 2 terms, I get the same expression in the parenthesis, 1 plus y or y plus 1. You can factor that 1 plus y out from those 2 terms. Left over will be x square plus 2. So looks like the right hand side of my differential equation can be rewritten in form of the factored form, where one of the factor can be seen as a pure function of y and other factor can be seen as a pure function of x. This is indeed a separable differential equation. And then the fourth differential equation, the last one, number 6 is not separable. So now that we know how to identify separable differential equations, I would like to now introduce to you how to solve the separable differential equation. So as usual, I am going to give you a general idea first to solve separable differential equation, and once we have this general idea with us, I am going to implement it with various set of examples. Alright, so suppose you are given initial value problem in terms of separable differential equation. So dy by dx is a function of variable x multiplied by function of variable y. So the right side can be seen as a factors of variable x and variable y. And let's say you have some sort of initial data associated with it. Alright, so when initial value of x is x naught, initial value of y is y naught. Remember, x naught, y naught are numbers, numerical values. Well, the first step what I would like to do here is separate the variable by the means of equality. Alright, again, this is the reason why this type of differential equations are called separable DE. You can separate the variable by the means of equality. Alright, so what I would like to do is I would like to send function of y on the side of dy, and I would like to move that dx on the side of function of x. Alright, so let's do the following. Multiply both sides by 1 over g of y. Alright, I get this particular expression that 1 over g of y dy equal to f of x dx. Alright, want you to notice that on the left side of equality I have a pure function of y along with dy. On the right side I have a pure function of x along with dx. This is something that can be done in a separable differential equation, and that is the reason why we call them separable DE. Variables can be separated by the means of equality. Alright, now in order to solve this differential equation, I would like to get rid of that dx and dy. This is clearly a differential relationship. Alright, remember, you have done something similar when you did integration by parts technique. Remember when you were asked to retrieve, for example, v from this differential relationship, you were integrating both sides with respective variables. Alright, and antiderivative of both sides was giving you, the value of v. Want you to do the same thing to solve the separable differential equation. Integrate both sides with respective variables. Meaning that integrate left side with respect to variable y, right side with respect to variable x. We have 4 basic integration techniques: direct matching, algebraic simplification, U substitution, and integration by parts, and spatial substitution. Assume that we know how to integrate 1 over g of y and f of x. Suppose we can integrate both of this side using existing integration techniques, and let's say antiderivative of g of 1 over g of x is capital G of x, 1 over g of y is capital G of y, antiderivative of f of x, let's say it's capital F of x. Alright, I want you to do is calculate antiderivative of this function. Suppose it's capital G of y, antiderivative of f of x, suppose it is capital F of x. Now once you get these two antiderivatives, I want you to set them equal to each other and throw a constant of integration to it. What you get is called the general solution of given differential equation. Alright, so computing general solution of separable differential equation is not that bad. I would like to mention here that this c is a generalized constant of integration. It could take any values between negative infinity and infinity. So this is not just one solution, it's an infinite set of solution. Assuming that we have infinite choices for c, each different choice of c will create one brand new solution of our differential equation. So understand that why we call it general solution. It's an infinite set of solution. Every particular c value gives you one brand new solution of your differential equation. Alright, and that's the infinite family. So we call it general solution. So let's keep that in mind. Now let me tell you how this initial data can be used to obtain one very particular solution that goes through the initial data. Alright, so this is set of infinite solution. It is a function of y, x, and then you have c. Alright, if I supply you the value of x and y in terms of numbers, then convince yourself that it is possible to compute the value of c. Alright, so let's do it here. Use x0 and y0 in general solution and obtain a particular value of c. Alright, when you throw this particular value of c into your general solution, what you get is called particular solution. Again, to get the particular solution, you will have to throw this particular c value that you obtain by throwing this initial data into general solution. Into that general solution itself, you get a particular solution. Okay, and now we will try to see few examples.